This is Suvarchala, working as an associate professor in the Department of Computer Science and Engineering in Institute of Aeronautical Engineering. As a part of the Database Management System lecture series, in this lecture, I would like to discuss about the deadlock handling related to the concurrent transactions. Concurrent transactions means the transactions are going to be processed in database management system simultaneously. That is one of the major advantage of our database management system. So while processing these transactions simultaneously, how the consistency of the database is going to be maintained, and as a part of that, we already discussed in previous lectures related to the log-based protocols and how the logs are going to be allocated so that consistency of the database can be manageable. So, to enforce isolation and consistency in concurrency control, we have to take care of the database management system concurrency control concepts in detail so that read-write and write-write conflicts of logs can be easily resolvable actually. The concurrent execution, in a concurrent execution, if a transaction T1 conflicts with T2 over a data item A, then the existing concurrency control decides if T1 or T2 should get that particular data item, and if the other transaction is going to be rolled back or awaits until that particular data item is going to be released by the transaction for which it was allocated actually. That means the concurrency control component will decide it actually. Various protocols are there in implementing this concurrency control management. Among these protocols, we already discussed about the log-based protocols. That means in this protocol, a log mechanism is going to be implemented by the concurrency control component. That means to access any data item, depending upon the requirement of the data item, two types of logs are going to be allocated to the respective transactions. Those two logs are exclusive log or shared log. If the data item has to be undergone a write statement in the particular transaction, exclusive log is requested by the respective transaction. Only the data is reading and is not going to be updated by the respective transaction, then shared log is going to be requested. So depending upon the log requests are made to the concurrency control manager by the programmer, the respective logs are going to be allocated. Or sometimes what happens, the programmer need not know all these things. Specifically related to the concurrency control manager will decide which transaction has to be executed, which logs are to be requested, and which logs are to be allocated, etc. These transactions can be proceed only after whatever the requests are made by the transaction, all those logs are granted, then only the transaction starts execution actually. And also we discussed various variations of two-phase locking protocol are available to us. Basic version and conservative version. In case of basic version, transaction locks the data items incrementally. And in case of conservative version, to prevent deadlock, all logs are going to be desired data items are going to be requested and acquired before the transaction begins itself, whenever it is going to be or wherever it is going to be used actually. So another version of this two-phase locking protocol is a strict two-phase locking protocol. This is more generally used in most of the softwares actually. This version in this basic algorithm where unlocking is performed after a transaction terminates, that is after commit statement is going to be executed or aborted or rolled back, then only unlocking process is going to be started. This is the most commonly used two-phase locking algorithm in most of the softwares. Fine. While allocating these logs, sometimes the transaction may enter into the deadlock state. what is this deadlock state and how to handle this deadlock state actually. For example, in the current example, you consider two transactions are there. The two transactions are here. T1 is having write X and write Y. T2 is having write Y and write X. The schedule of these two transactions may be like this. Let us assume that lock, because write is required now, so exclusive lock is requested on X and this transaction is writing X. After completion, it may request for, because before write only it may request. Meanwhile, transaction 2 entered, so it requests for the exclusive lock on Y and it start writing that particular write. So this is Y. It start writing Y, right? So this exclusive lock is going to be considered here, so that what happens, the respective algorithm is going to be written by the respective locks are going to be requested. Now, what is the next statement of or next operation of T1? T1 is write Y. Write Y means this T1 is waiting to get an exclusive lock on Y. Coming back to the T2, T2 completed on X, that is exclusive lock on Y, and it is doing, then it is waiting to release the lock, that is wait for lock X on. That is exclusive lock on X because of this write statement. Now, what is the situation? Because being a strict two-phase logging protocol, no locks are going to be released till the commit or abort or whatever may be the operation, the transaction completes actually. Right? So that's why whatever the lock, whichever the locks are held by the T1, that is now in this example, exclusive lock on X was held by T1, exclusive lock on Y was held by T2. Now what the status of T1 and T2? T1 is waiting for exclusive lock on Y, which is already held by the T2, and T2 is waiting an exclusive lock on X, which is already held by T1. That means both are waiting here. So in this example, that means here T1 is waiting till T2 completes and T2 is waiting till T1 completes. Why? Because it has to release the respective lock. It may never happen actually. That status is known as a deadlock status. Right? So that's why in the current example we are reading Y and writing X. While coming to the writing X, then it is T1 and T2 not follow the two-phase policy, but they are in deadlock. Two-phase policy means they are not releasing any locks. Only acquiring phase is there. So that's why two-phase locking protocol, once the it enters the release of the locks, then automatically it cannot acquire. No? So that's why you are going to, the respective transactions are waiting, acquiring the locks on the other data items actually. Now this status is known as deadlock. T1 and T2, two transactions are in the deadlock state. The system is deadlocked if there is a set of transactions in a system such that every transaction in the set is waiting for another transaction in the set to be get completed. That means this example was explained by using two transactions only. In a schedule, there may be n transactions also. So among all these n transactions, all transactions may be in the deadlock state. One may be waiting another one, another one, another one, another one, another one. This is a cyclic process till the last one waits for the first one to get completed, which never happened. So that's why how this concurrency control manager will take care of that otherwise. Otherwise, the concurrency control manager component will take care of the situation or handles that particular situation. Deadlock prevention, there are various techniques are there. First one is deadlock prevention. As far as possible, we will assure that the transaction schedules may not enter into the deadlock environment at all, or a problem of deadlock it may not enter. Such a way, that means we will, prevention is better than cure. No? So that's why we would like to prevent the transactions may not enter into the deadlock action. That means the protocol ensures, this type of protocol ensures that the system will never enter into the deadlock state, and various strategies will be there for that actually. So by approaching or by following these strategies, we may assure that the system may not enter into the deadlock. So it requires that each transaction logs all its data items before it begins execution. So generally what happens, whenever any requirement of operation is there on a particular data item, then the logs are going to be requested. But to prevent it entering into the deadlock state, one technique is whichever the data items are used in our transactions, on those all data items, all logs are going to be requested in the beginning itself, and till the transaction completes, they may not release them. So it may not wait for any log, no? So it may not enter into the deadlock. But there may be some problems, other problems will be there actually. In such cases, some transactions which are required logs on these items have more queue will be there in waiting state actually. The conservative two-phase locking protocol uses the same approach. By using the same approach, we can prevent a deadlock. And another technique is there. Impose partial ordering of all data items and require that a transaction can lock data items only in the order specified by the partial order. This is a graph-based protocol. So by using the partial order of this locking, we can avoid the deadlock entering into the deadlock stage. And some more strategies are there. There are schemes or strategies we will consider. Deadlock prevention strategies, which depending upon the deadlock possibility, occurring of the deadlock state possibility, the prevention is going to be done. In both of these previous cases, waiting state will be more actually. In the first case, that is accepting, or that is conservative two-phase locking protocol, accepting all logs before the transaction starts itself and release the logs after completion only, waiting state. Even in graph-based protocols also the same problem may occur. So that's why some other strategies are there. One them is a wait and die scheme. This is non-preemptive, right? That means in wait and die scheme means a transaction may be waiting for a particular data item over a period of time. And older transaction will wait for younger transaction will release the data item. That means older transaction is waiting. Older means the transaction which is entered earlier. So the transaction may be waiting for data items which are held by the younger transactions to release that particular data item. But younger transactions never wait for the older ones, they are rolled back instead. By using this up to certain extent, the deadlock can be prevention. That is, younger transactions may not wait if the data items are held by the older transactions. But if it may wait for the data items which are held by the younger one to them, then entering into deadlock is very, very rare actually. Such a way we can prevent actually. A transaction may die several times before acquiring needed data item. So if a younger one won't wait till the older terminates, then automatically what it's supposed to do? It has to roll back so that it will restart again. That means certain transactions are going to be rolled back based upon this timestamp allocated to the respective transactions actually. That is, older transactions will wait for younger one to release the data items, but younger one won't wait the older transaction to get released, but they will get rolled back. Once they get rolled back, what happens? They will release all data items for which the older transactions are waiting. They maybe get served actually. But what is the problem with that? Generally, a transaction may die several times before acquiring needed data items. Because more older transactions takes more time to execute or to complete the transactions, then automatically the younger transaction will keeping on roll back because of this timestamp actually. It won't get a data item which is held by the older one, no. So always it will be same transaction, same younger transaction may be rolled back multiple times. And the second scheme is there, wound and die. That is what is the first one? Wait and die. It is waiting, older or waiting, and younger or die. Right? Dying means roll back, no? So that's why it's restarts actually. Wound and wait scheme. It's a preemptive scheme actually. So preemptive scheme means it will make it as a forcibly roll back. In this wound and wait, older transaction wounds here. That is, forcibly they will roll back of younger transactions instead of waiting for it. Reverse one. That is, in this example, in this scheme, older transactions will be rolled back instead of waiting for younger transactions to get released the respective locks or required data items. But younger transaction may wait for older ones. In this example, older transactions may be rolled back, no? So those are wounds actually. Maybe fewer rollbacks than wait and die scheme. Why? Because older transactions, no, even they are rolled back again, they'll start, no, by that time this younger transactions may get complete. So that's why same transaction roll back multiple times occurs, but the number of times is going to be comparatively less actually. In both of these two schemes, a rollback transaction is restarted with its original timestamp. This is the specific note we have to always remember. Both, whenever rollback, automatically when it starts, a new timestamp supposed to be considered. If it a new timestamp is considered, then automatically it will be considered as a very, very younger one. But whenever rollback transaction is restarted, and the restarting will be done with its original timestamp, so that it will be considered as an older one over a period of time. Older transactions that therefore have some precedence over newer one. So any new transaction is submitted now, the older transaction was rolled back, that remains as a older one only, no. So because of that, what happens? Starvation can be avoided actually. Older transactions have precedence over the newer one always. Even though they are restarting, they will be treated as a older one only, and the starvation can be avoided. Similarly, another scheme is there. Time-based schemes will be there. In case of time-based scheme, whenever a transaction is waiting for a particular transaction to get complete or a release lock, a timestamp is allocated. After that particular timestamp, it will be rolled back automatically. That is, a transaction wait for a lock only for a specified amount of time, maybe some seconds, right? And those are going to be rolled back once after the time elapsed, it will roll back again, it will restart. So that deadlock can be prevented. So the deadlock, even though deadlock occurs, what happens? Some of the transactions are going to be rolled back because of this timestamp waiting, and it is very simple and to implement this type of technique also. But in this example, starvations are possible always. Why? Because the timestamp whenever same transaction may be rolled back more number of times. So starvation is possible, and it is difficult to determine how much time should be allocated, how much time slot is to be allocated as an interval actually. Deciding of that time slot is a little bit considered as a difficult task actually. Right? Properly it has to be set so that the transaction may not wait for a longer period, as well as may not enter into a starvation state for a longer period. Deadlocks can be described as we can do another one. How can you detect whether a deadlock occurs or not actually? So till now we discussed the preventive techniques actually. Fine. But first, if any schedule was entered into the deadlock state, then it has to be identified, then only we can apply some technique further. So a deadlock can be described using a wait for graph, which consists of a graph means consists of set of vertices and edges. What are these vertices? Vertices are set of transactions in that particular schedule. All transaction in the particular system is known as V is a set of all vertices. Each vertex represents a particular transaction. If 5 transactions are there, 5 vertices will be there. And there will be set of edges. What is E? There will be an edge between a directed edge between Ti to Tj such that if Ti is waiting for a Tj to release a data item, if Ti is waiting to release a data item by Tj, then there will be a directed edge from Ti to Tj. That means Ti is waiting for the Tj to be released some data item. Like that, if you able to draw a graph depending upon the all transactions and all waiting, if that particular graph consists of a cycle, you can say that the system of transactions are entered into the deadlock state. When a T requests a data item currently being held by Tj, then an edge Ti Tj is inserted in the wait for graph. If this edge is removed only when the Tj is no longer holding a data item needed by the Ti. That means this graph is keeping on changing. The edges are going to be added, the edges are going to be repeated depending upon the waiting of a particular graph releasing a data item by some other transaction. So this graph structure, number of vertices will be fixed only, but the edges are going to be added and deleted depending upon the waiting. The system is in deadlock state if and only if a wait for graph has a cycle. So a deadlock detection algorithm generally periodically checks whether there is a cycle in the graph generated currently. For example, consider in this wait for graph, in the first case, you observe T26 is waiting to release a data item by T28. T25 is waiting for release a data item by T26. Similarly, T27 also waiting for T26 to release a data item, and T25 waits for T27. There is no any deadlock state. There is no mutually, a cyclic waiting is there. So that's why in this wait for graph, there are no cycles. Please observe. So that's why there is no deadlock in this set of transactions. But coming to the next second case here, if you observe, T25 is waiting for T26 and T26 is waiting for T28. Again, T28 is waiting T27 and T27 is T26. You observe these three. That is T26, T28 part. This forms a cycle. So that's why there is a deadlock. You observe, this is waiting for this is waiting for this. That is 28 is waiting for 27, 27 is waiting for 26, again 27 is for 28 in turn. A cyclic process. So, like that we can, if a wait for graph consists of cycles, there may be a deadlock situation. I have used the word starvation a long number of times during this deadlock process. What is starvation? Starvation means here, it occurs when a particular transaction consistently waits or consistently rolled back or restarted and never gets a chance to proceed further. Then we can say that particular transaction is in starvation. It requires some status actually. It requires some completion of the transaction, but it never get complete because always it is waiting state or it may be restarting or a rollback and it never gets a chance to proceed further, it never automatically complete or could not able to complete the transaction itself, then we can say that the transaction is in starvation. Whenever we are doing this in resolving these deadlock situations, there is a possibility of, already we discussed some of these techniques. In those techniques, we in wait and die or wound and wait or timestamp. In all these things, some transactions are going to be rolled back. In this deadlock resolution or prevention techniques, always it is possible that same transaction may consistently be selected as a victim and always rolled back. It happens sometimes. So same transaction is always selected to get rolled back. Then what happens? The transaction never gets a chance to get complete. Then it is entering into starvation. This limitation is inherent in priority-based scheduling mechanisms. So priority means least priority will always wait. Priority based means whenever the least priority transactions are there, then priorities were decided. Such transactions, always the least prioritized transaction will be get served late. So that's why it may enter into the starvation. In wounded wait schemes, younger transaction may always be wounded, that is aborted in by long running older transactions, which may create starvation of the younger one. Why? Because the older transactions may be executing for a long period of time, then the younger one always will be younger, no? So then always it will be restarting, that is rolled back in, then it may enter into the considered as a starvation state. So we discussed preventive techniques. As far as possible, the deadlock preventive manager will take care of how to prevent the respective deadlock state, entering into deadlock state by a set of transactions. And also we discussed how to detect a deadlock by using wait for graph. Once we understood that, that is concurrency control manager identifies there is a deadlock among these set of transactions, then recovery must be considered. When the deadlock is detected, then it has to be recovered. How to recover? One of the transactions should be forcibly rolled back. Then the deadlock situation is going to be break. So some transaction will have to be rolled back. That means some transactions we have to make as a victim to break the deadlock. Select the transaction as a victim, because of which the minimum cost is going to be considered, which will incur minimum cost. Restarting of the transaction incurs minimum cost. Such transactions generally will be selected by the deadlock recovery manager, so that those are going to be rolled back so that deadlock state can be break out. So the deadlock state is going to will be broken by using this recovery technique, that is rollback. While doing this rollback, how far this transaction has to be rolled back? Whether the entire transaction is supposed to be rolled back or partial transaction, that means up to the state where the deadlock can be avoided or deadlock can be recovered. So rollback, total rollback, two techniques are there. How far that particular transaction can be get rolled back, either entire transaction or partially. So that is more effective rollback transactions only as far as necessary to break the deadlock. That is enough for us. Because of this, in this such recovery techniques also, starvation happens most of the time. If the same transaction is always chosen as a victim, then that particular transaction is entered into the starvation state. It never gets a chance, no? So that's why we will consider it as a starvation state. Right? So that's why to avoid this starvation state, we may include how many number of rollbacks are done by each transaction. Depending upon that also, victim can be selected. It is the number of rollbacks in the cost factor to avoid the starvation will be included, so that more number of times already rolled back, for example, 5 times, 6 times will keep. Next time again comes, it is a victim, it won't be get selected. Another one, the next transaction which is having minimum cost, that will be selected actually. So that the starvation can be avoided while recovering this deadlocking actually. By using this deadlock preventive techniques as well as detection techniques and recovery techniques, the concurrency control manager will make the transactions, a system of transactions are going to be always executing in a proper manner, in isolation manner, as well as making our database consistent state, assuring the database consistent state, and assuring the transaction isolation execution. Right? So, because of these deadlocking techniques, always the transactions which are waiting for other transactions in turn can be avoidable. And most of these deadlock concepts are related to the operating system, in which operating system, the allocation of resources to the process can be having or entering into the deadlock situation. The same things are applicable to transaction management also in concurrency control. Thank you for watching this video.
Like, share and subscribe. Hit the bell icon for more updates.